the Inns of Court in London, home of the British law for more than 600 years, and curiously enough, the only place in Britain where you can still see gas lamps lit the traditional way, by a lamplighter with a pole. Quaint, isn't it? To us, gas lighting is no more than an interesting historical oddity, something for the tourists and the guidebooks. But to the Londoners living in the 1800s, it must have been a near miracle, rendering the streets of London safe for the first time. What the Victorians couldn't have recognized, that gas meant more than lighting, and that by a devious and complicated route, it was going to lead to the conquest of disease. The method of making coal gas for lighting was really very simple. Coal was heated strongly with the exclusion of air, otherwise it would have caught fire, and in doing so produced gases and vapors which were conducted along this pipe and bubbled through water to wash it, producing ammoniacal liquor and coal tar. And what was left was coal gas which burned with a luminous flame, like that. Gasworks very rapidly spread through the whole of Europe, producing vast amount of coke, and an apparently quite useless substance to them, this coal tar. This is admittedly a very unattractive, smelly substance from which can be made fertilizers, plastics, drugs, and even perfumes. In fact, it provides the basis for the whole of the organic chemical industry. In early 19th century Britain, the chemical industry hardly existed at all. It was thought a dirty and smelly pursuit, unfit for gentlemen. In Germany, however, enthusiasm ran high for the infant science. At Professor Liebig's laboratory in Gießen, pupils flocked from all over Europe to attend practical demonstrations. The greatest of them all was August Wilhelm Hoffmann. He's the one in the stylish top hat and frock coat. A brilliant and flamboyant individual, Hoffmann came to England in 1845 as director of the newly founded Royal College of Chemistry in Oxford Street, London. 8 years later, in 1853, a young man called William Henry Perkin came to study at the college. He was passionate about chemistry and hero-worshipped Hoffmann. When the master said he would like a method of synthesizing quinine, Perkin tried hard to oblige. The structural formula of quinine was not known, so Perkin had a pretty good idea of the number of carbon, hydrogen, and nitrogen atoms which it contained. Now, aniline, a product derived from coal tar, contained about half as many atoms. And Perkin, perhaps rather naively, thought that if he could persuade two aniline molecules to join together, he might get quinine. Now, the first step to promote this reaction was to treat some aniline with concentrated sulfuric acid. Really rather spectacular, and it fumes away to make aniline sulfate. His next step was to dissolve the aniline sulfate in boiling water, and then to treat the resulting solution, which I've got in the beaker here, with a powerful oxidizing agent called potassium dichromate. And quite soon, the solution will start to darken as a black compound forms. When Perkin filtered the liquid, he got a black powder like this. Now, whatever it wasn't quinine, but he tried to discover its chemical identity by testing its solubility. It wouldn't dissolve in water. When he tried an organic solvent, something rather remarkable happened. Now, what we have is a rather beautiful purple solution. Now, just as Perkin was aware of the fact that the world needed quinine, he was also aware of the fact that the textile industry needed a good purple dye. So I suppose he must have said, I wonder, and tried to dye a piece of cloth. By accident, he had made the world's first synthetic dye, aniline purple. Before Perkin, dyes came from natural sources, like this plant indigo, which makes a blue dye. The woad plant also makes a blue, which ancient Britons used to smear on their faces. Whilst the root of this plant, madder, produced a red dye, which was used on French soldiers' trousers. Our boys, however, used an animal source for their red, the cochineal beetle. But the most difficult color to make by far was purple. That's why Roman emperors used it on their togas. In the ancient world, it was the Phoenicians who traded in dyes. Their cloth, dyed with Tyrian purple, was famous all over the Mediterranean. They made the dye from the body of a sea snail, murex, and it was expensive because it needed over 6,000 snails for every gram of dye. In Perkin's time, purple was made from the lichens on the rocks at the seaside, but the pale lilac they produced was unsatisfactory. It was faded by light and removed by washing. Perkin sensed that his new aniline purple might fill a gap in the market, so he sent a sample to one of the foremost dyers of the time, Pullers of Perth. In their reply they said, "It is a color which has been much wanted." Perkin needed no second bidding. Aged only 18, he set up a factory at Greenford in West London to manufacture the dye. Within months it was a rage of Paris, where they called it Movine. But Perkin had really arrived when Queen Victoria wore a dress dyed in Movine at the Great Exhibition of 1862. I can't guarantee that this is a dress actually worn by Queen Victoria, but it does illustrate the gorgeous shade which can be obtained on a lustrous fabric using Movine. Now here's a filter paper, which I used to filter off the precipitate of the Movine I made earlier on. If you compare the shade at the edge of the filter paper with a fabric which I had 120 years ago, it really is a remarkable match. I wonder, madam, if you could just hold this for me for a moment. Now, the cookery which was involved in making Movine didn't actually solve the dye manufacturer's problem, because it didn't give them a general method of making dyes of all sorts of different colors. It wasn't until 1859 when Peter Gries, at the time working as a chemist in a brewery in Burton-on-Trent, again using aniline, actually solved the problem. What he did, by a series of chemical tricks, was to turn the aniline into benzene diazonium chloride. We've got some of it here, which has to be kept cold. Now, the diazonium salts are rather special in that they have a hook on them, to which it is possible to couple other compounds. This is an illustration of it here. And once we've done that, we have a dye. Now, what I've got here are 8 beakers containing 8 different coupling compounds. A little from each beaker has been poured out into these petri dishes. If I now take a small quantity of the benzene diazonium chloride and add it to the first one of these petri dishes, we get a brilliant yellow dye. Chemists now got busy and synthesized a whole range of diazonium salts, an even bigger range of coupling agents, and the world burst into a riot of color. Unfortunately, as far as Britain was concerned, that was the end of the story. Perkin didn't like business and gave up in 1873. Hoffmann had already retired to Germany in 1865 to become professor of chemistry in Berlin, and Peter Gries and all the other bright young men went with them. The dye industry in Britain declined, whilst in Germany, new dye works were springing up all over the country. On the banks of the River Main, just west of the industrial city of Frankfurt, lies the little medieval town of Höchst. Lying by a ford on the river, it has made its name as a customs post before the unification of Germany. Now the dye makers, Meister, Lucius and Brunning, had built a dye works outside its walls. In the future, this firm was to develop into the massive Höchst chemical combine, mainly because down the road in Frankfurt lived a doctor, Paul Ehrlich, who developed some novel uses for the new aniline dyes. Ehrlich didn't use the dyes to color fabrics, he used them to color people, or at least bits of them under the microscope. Ehrlich was an expert on dyes and one of Germany's greatest scientists. A workaholic, he smoked 25 strong cigars a day and lived on a diet of mineral water. He was exceptionally untidy, and his office was a sea of paper. He had spent his early years working with another pioneer, Robert Koch. Koch started as an obscure Prussian GP with an interest in infectious diseases. Working with a microscope, given to him as a present by his wife, he had shown that anthrax, a disease of man and animals, was due to tiny rod-like bacteria called bacilli. Koch had been a medical officer in the Franco-Prussian War and knew how many men were killed, not by bullets, but by the infection of wounds. He took specimens of the pus from wounds and stained them with the new aniline dyes. Down amongst the big red pus cells, he saw tiny white spheres. These were a new class of bacteria, the cocci. Koch was able to isolate these cocci and grow them, showing how one type, the streptococci, stuck together in chains, a deadly necklace. But Koch's greatest triumph was yet to come. In 1882, in the lecture hall of the Berlin Physiological Society, he demonstrated the cause of tuberculosis, the dainty but deadly tubercle bacillus. Lodged deep in the tissue of the lung, it was only shown up by brilliant pink dye. The young Ehrlich helped Koch to develop this dye and was associated with him off and on for the next 17 years. In 1899, Ehrlich came to Frankfurt to the Institute of Experimental Therapy, now known as the Paul Ehrlich Institute. In his mid-40s, he was already famous for his work with Koch and Behring on vaccines and antitoxins against diseases such as diphtheria and tetanus. These proved to be remarkably effective against bacterial diseases, but they seemed to be a class of organism against which vaccines had no effect whatsoever. These are the protozoa, minute single-celled animals, larger than the bacteria, although still tiny. This is one of them, the trypanosome, swimming between the red cells of the blood. It causes sleeping sickness in man and animals and is impervious to vaccines. Since vaccines were of no use against protozoa, Ehrlich decided that he would have to find a chemical which would kill the protozoa inside the body without at the same time harming the host. Now, where to find such a magic substance? He turned his mind again to his knowledge of dyes, and particularly to his knowledge of Vitis Stains. So far, dyes had largely been used to stain dead material. Vitis stains are capable of staining living cells differentially. This means they stain some of them and not others. Here are two specimens of human blood. Let's leave one alone, and to the other we add a Vitis stain. This is methylene blue. Mix it up a bit, then leave it to stain for a while. Now let's put the normal one under the microscope. Here we can see the red blood cells. They're clumped together a bit, probably because the slide is drying out. But the cell I'm interested in is this one here. I just move the slide to bring it into the center. That colorless cell is a white blood cell, used by the body to fight infection. Let's see what it's like with a Vitis stain added. Now this is a stain specimen, and you can see that the red cells haven't taken up the dye at all, but the white cell has, a very marked blue color. Trypanosomes take up the dye in the same way. You can see two of them in the center of the field, and again the red cells are unstained. High doses of the dye kill the parasites altogether. And since it did not touch the red cells, Ehrlich wondered if this might be a way of killing trypanosomes in the human body. To test this, he infected mice with trypanosomes and then dosed them with a dye to see if it would cure the illness. It was very tedious work, with many weary failures. But in 1904, the 305th compound was found to kill trypanosomes in mice and horses. But it was a false dawn, because compound 305 proved to be too toxic for use in man. But in that year, another discovery was made, which was to completely change the direction of Ehrlich's work. In Berlin, Schaudin and Hoffmann showed that the unmentionable disease, syphilis, is caused by a delicate organism called Treponema pallidum. Since it was mobile and quite unlike a bacterium in appearance, we thought it was related to the trypanosomes, so Ehrlich included it in his research program. For his experiments on syphilis, Ehrlich was aided by a young graduate from Tokyo University, Dr. Harter. For 6 years, this tiny laboratory served as the headquarters of Ehrlich's quest for the magic bullet. This is a stool, this is a microscope, this is a bench where he worked. And he used to say, give me a Bunsen burner, my dyes, and some filter papers, and I can do anything. Actually, it took another 300 compounds, the results painstakingly recorded in these laboratory notebooks. Until 1909, his assistant Harter told him that compound 606, and I've actually got some of the original material here, did actually and definitely cure syphilis in rabbits. Ehrlich was pretty wary at first, but a series of experiments in humans did show that compound 606 would cure syphilis in man, usually with only one injection. From now on, the whole staff of Ehrlich's laboratory slaved at making compound 606. In the 6 months after the discovery, they produced 65,000 doses of the drug before manufacture was taken over by the much expanded Meister, Lucius and Brunning. The trade name they chose was Salvarsan, and it was the first drug in the history of medicine to kill bacteria inside the body. The trials and tribulations of Salvarsan left Ehrlich a spent man. A daily diet of cigars, overwork, and the advent of World War I took their toll. And Ehrlich died of a stroke at the early age of 61 in 1915. Fortunately, one of his pupils was able to take the story of dyes and drugs on into the next chapter. That chapter was to unfold in the North German town of Elberfeld, which, apart from a decent-looking Rathaus, has little to commend it except its overhead railway, the Schwebebahn. Elberfeld lies in the valley of the river Wupper, and it was here that Friedrich Bayer started his dye works in the late 19th century. It expanded rapidly, and in 1910 it took on a new scientist for drug research. Wilhelm Röhl had worked with Ehrlich on trypanosomes, and he continued his research at Bayer. Over 10 years, he tested more than 1,000 compounds before he found one which would kill trypanosomes. This was marketed by the company with characteristic national modesty as Germanin, or more correctly, Germanin. The protozoa were in retreat, but the bacteria remained unconquered. Unconquered, that is, until the arrival at Bayer in 1927 of Gerhard Domack, a pathologist from the University of Münster with an interest in immunology. This laboratory, now used by Bayer for the control of atmospheric pollution, served as a pathology block in Domack's time. Here, between 1927 and 1932, he patiently tested hundreds of compounds made by biochemists. One of these, a red azo dye called Protozoa, originally intended for coloring leather, proved to be quite dramatically successful in curing mice of streptococcal infections. For trials in humans, it was put up as tablets, and here is some of these tablets in their original packing. Their use proved to be equally effective in humans, and to add to the drama, one of the early patients was Domack's own daughter, who, when she was 4 years old, was dying of a streptococcal infection. The drug was administered to her, and she was cured 2 days later. Protozoa is a red azo dye, and it was thought that the mere fact of being a dye was an important part of its action against bacteria. This was found subsequently not to be true. You'll remember that when I was talking about azo dyes, I said they were made out of two components. Here's a model of the Protozoa molecule consisting of a large part and a much smaller part. It was found that by separating the smaller part, called sulfonamides, that this was just as effective as the whole molecule. Now sulfonamide is a member of a much larger family of drugs called the sulfonamides. The sulfonamides rapidly achieved international acclaim. Franklin D. Roosevelt Jr., son of the American president, was cured of pneumonia. At Queen Charlotte's Maternity Hospital in London, deaths from the dreaded childbirth fever were reduced from 23% of cases to 5% in 1 year, and many more babies went home with their mothers. Then, right in the middle of World War II, the old bulldog himself was struck down with pneumonia. He was treated with a sulfonamide called sulfapyridine, or MNB 693, and made an uncomplicated recovery. In a broadcast to the nation in September 1943, he said, "This admirable MNB, from which I did not suffer any inconvenience, was used at the earliest moment, and after a week's fever, the intruders were repulsed. The age of antibacterial drugs had arrived, and the dye factories of yesterday became the great drug companies of today."